Welcome back to STEM Online Academy. My name is Jason Masterakos. I am the founder of STEM Online, where we specialize in helping undergraduate students who are taking courses in calculus, linear algebra, and physics courses with hard midterm and exam preparation. Okay, so let's get right into today's lesson. I mentioned yesterday that today would be a problem-solving day. We're going to be looking at a particular interesting summation. It's this sum right here. Okay, we're going to be looking at this guy. All right, this one right here, putting an asterisk right over it, and it's the sum of 1 all over 2n minus 1 all squared is equal to pi squared over 8. We want to be able to prove that that's the case. Okay. Right. So why are we looking at this sum today? That's because most students do not get stuck on this series because the algebra is too hard. It's not an algebraic problem. I want to bring up this specific problem for a reason. They mainly get stuck because they do not know what to do first, right? I've mentioned this before in my other math videos, especially when the math gets a bit more abstract after grade, 11 or whatever. You need to have a sixth sense. You have to develop a strong sixth sense for doing algebra or anything, right? Any type of mathematical discipline, right? So that's what I want to help you with, is to develop that sixth sense, right? Now it takes a while. This takes a lot of solving problems, right? But you can develop it. So as I said, you guys mainly get stuck because you do not know what to do first, all right? So let me give you an example, right? What I mean here for this specific case, right? They see, for instance, students will see this. Most of you will have this problem, okay? Most of you will see 1 plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared, for instance, plus dot, dot, dot. This is some sort of infinite series, okay? And they just know that the answer somehow becomes, right, pi squared over 8, okay? That is not good enough, okay? Because you haven't provided a reason as to how you know that you get to the pi squared over 8, right? You're better off actually having some sort of reasoning to an incorrect answer than having no reasoning to an answer that you remember that happens to be correct, right? The point is that you need to know how to derive and get to the final step. Otherwise, it's pointless. Okay. So let's get right to that, right? Right, because this number feels like the number just falls out of the sky. It just feels hand wavy. The argument that I made, I just said all this, and somehow magically the pi squared over 8 comes out, right? Okay, and that's problematic. Okay, so there's a very clean structural reason why this happens, how we get to that pi squared over 8. And in this video, I'm going to show you exactly the exact trick that a lot of you will miss, so that the series stops becoming as intimidating, stops becoming magical, and starts feeling more of a logical construction. Okay. All right. Let's try it. Okay. So let's look at this. All right. So the first thing we want to do, right, is we want to prove the following. Okay. So remember, we were trying to prove this, right? So we want to prove the following summation. Okay. We want to prove that the sum from n equals 1 to infinity of 1 all over to n minus 1 all squared equals pi squared over 8. Okay? This sum is the sum of the reciprocals of the odd positive integers squared, if you've noticed, right? So for this proof, first thing we're going to do, right, is we're going to explicitly notice this, right? That this is just 1 plus 1 over 9 plus 1 over 25 plus 1 all over 49 plus dot, 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 dot. As I mentioned, that this is the odd integer squared, right? That's what the summation is saying here. Okay. Now, if you've seen the Bessel problem before, by the way, I have a video on the Bessel problem. If you want to look at that first, it might be handy. Then you'll know where I'm getting this result from. You'll know that we know that. So we know. I'm just going to say we know that the Riemann zeta function, right? So Riemann zeta, zeta. Just 1 second here. Zeta of 2 of the summation from n equals 1 to infinity of 1 all over n squared is equal to pi squared over 6. This is a special result. Okay. You should have at least seen this series, even if you haven't seen my video on the Bessel problem. You should have at least seen this series maybe come up in a calculus 2 class, at least. Even if you haven't solved problems with it, at least if you know it, you've seen it before, that's all you need, right? As long as you have all the other tools, right? The point of this, right, is to make sure that just because you haven't seen a problem before doesn't mean that you sort of know how to figure it out. As long as that problem requires the prerequisites that you have, which my videos do, all the others, just like, calculus 1, calculus 2, linear algebra prerequisites from, from the previous class, you should be fine in being able to solve it. The only difference between my videos is that these problems are tricky. Okay, they're not straightforward. All right. So this is the real doorway into this problem. Okay. Now notice how the odd term sum becomes easy once you stop trying to attack it directly. Okay. That is the first major lesson. Okay. All right. So the exact mistake when it comes to this type of problem that students make, they try to force the odd term series directly. Okay, don't do that. If you do that, you're going to go down the wrong step, and then the whole thing is just not going to make any sense. You're going to go in circles. Okay, and that is why the problem feels harder than it actually is. Okay, because a lot of you will probably be asking what I think you would be asking anyways, is that, do I need a Fourier series immediately? Okay, I know that you're thinking that because right when you see the summation with an index starting from 1 to infinity, you're thinking, I may have to use a Fourier series, or I may have to use Percival, or whatever. Number 2, do I need a special trick? Right? That's another thing you guys ask. Number 3, do I need to guess a function? All three of these things, all three of these assumptions, um, no, they're not going to. I mean, sometimes these methods work, right? If you need a Fourier series immediately, do I need a special trick? Do I need to guess some sort of function f for some reason? Sometimes they work, but the cleanest way to do this is much simpler. Okay. So we're going to start with the full reciprocal square sum of the square, and then we're going to subtract the even terms. This will make more sense when I do this. Okay. That's the structural approach here. Is we need to somehow subtract away the even terms, so odd from the even terms. Okay. Hope you're appreciating. Problem looks cool. Okay, so that's the way we're going to do this, right? So this is not really a problem about summing out just the odd terms. As I mentioned, I was taking the odd terms of this series here, right? This series right here that I'm putting in asterisk. Okay. It is a problem about splitting the known sum correctly. There's going to be odd and even terms to this summation. Okay. So you need to be able to group them correctly. If you group them correctly, you should be able to solve this problem. And that is why this video matters for exam, right? That's the hard part is not the calculation, right? Right. That's not the hard part, right? The hard part is recognizing the structure and the reasoning. Okay, that's the hard part. Calculations are if it was just calculations, then it would be easy. It'd be an easy course. Okay, so let's write the full series and separate it visually. All right, so let's begin. Okay, so let's begin. So let's let's begin. Okay, so we're going to begin with this. Okay, so we're going to say that going back, as I mentioned, this is called the Riemann zeta function. You haven't seen it before. Sum from n equals 1 to infinity of 1 over n squared. And this is equal to 1 plus 1 all over 2 squared, right? Plus 1 all over 3 squared. You should know how a summation works, right? I'm indexing from n equals 1, and then I increase by 1 for each n plus 1 in the summation. 1 3 squared plus 1 over 4 squared. And since this is an infinite series, I'm saying plus dot, 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 because it's infinite, okay? All right, that's the first thing. Okay, so we've got an interesting result here. That's a Riemann zeta function when our exponent is 2, right? So this is, in reality, we call this zeta at 2, okay? All right, let's go to the next page, okay? Now, we're visually going to separate this into odd and even terms, right? There's odd and even terms. If you thought there was only one or the other, you were wrong about that in that assumption. It's only odd or even, okay? So I'm going to take my infinite series, okay? So I take summation from n equals 1 to infinity, okay, of 1 over n squared. And this is equal to, I'm grouping now, the odd terms, 1 plus 1 over 3 squared plus 1 all over 5 squared plus dot, 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 okay? Make sure you put the dots there. If you don't have the dots, it's incorrect. Plus, on parentheses, the even terms, okay? So 1 all over 2 squared plus 1 all over 4 squared. Okay, so that's 1 second. So 1 over 4 squared plus 1 over 6 squared plus dot, 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 okay? Now, the first group is exactly the sum that we want. Look at the first group. I'm going to highlight this, by the way. This is the odd terms. This is the even. So I have odd and even terms for my summation so far, right? I've grouped them appropriately. Okay. Now, what you want to do from here, right, is let's call our original question, right? Our original question was 1 all over sum of 1 over 2 n minus 1 all squared, right? What we want to be able to do, okay, is we want to call this some variable, right? So I'm going to say here, let s as a function of n be defined as our infinite series, okay? It's good to define this as something. It's going to make sense as I do it. N equals 1 to infinity all over of 1 all over 2 n minus 1 all squared, okay? So now we have that. There's a reason why I did that. Now, this is where it gets a bit funny, right? There's a reason why I brought the Riemann zeta function earlier, this guy right here, and how it's connected to the 1 all over 2 n minus 1 squared. Okay, so you sort of have to have a feel for knowing what to use and what to compare what to what. Okay, knowing what to use is the most important, and then knowing what to compare is very important, right? Because I'm using here, right? You notice that the Riemann zeta function at s equals 2, that's this exponent here, okay, has a relationship to this exponent 2. So, and another thing too, you'll notice is that the index starts at 1, so this starts at 1 and goes to infinity. So you know that this has some relationship to the Riemann zeta function at s equals 2, okay? So what I'm going to do is I'm going to decompose this, okay? This may look odd at first, but I'm going to decompose that, all right? So let's write our sum like this. So now I'm going to say, now I'm going to write my sum, okay? I'm going to write my sum like this. So I'm going to say that the summation from n equals 1 to infinity. I'm focusing on the Riemann zeta function right now. Okay. Right, so I'm focusing on the Riemann zeta function. All right. And you will notice that this here is equivalent to S of n. S of n is what I've defined my summation here, 1 over 2n minus 1 squared. Okay, that's sum over here. That's what my S of n is. It's going to come handy in a second why I called it S of n. And then I'm going to add the sum from n equals 1 to infinity of 1 all over 2n all squared. In other words, I'm taking my original problem, S of n, right, plus an infinite series of 1/4, right, 1/4 of the original Riemann zeta function. Okay, let that sink in for a moment. I don't want to rush you in your understanding. There's a reason why I did that, because if I split up this summation, right, if I split up and decompose uh, my original Riemann zeta into this, right, you'll notice that if I add them, actually, if I actually were to add them, they would equate to this, actually, the sum of 1 over n squared. Okay, right? You can actually verify. I'm not going to do that right now, actually, because then it gets way too tech. It's going to be way too long. And I'm just summing up the important parts of the problem. Okay, but you can verify that on your own. And if you have any questions, you can always put it in the chat of the YouTube video. Okay, so now the whole problem has become full of sums, minuses, um, and every term contribution. This is already a much cleaner and much more elegant decomposition of the original problem. Okay, so from here on, right, what we're going to look at is we're going to evaluate the even term. Okay, so let's simplify the even term sum. Okay, so I'm going to simplify. So let's look at the even terms. Look at the even terms now. Okay, so taking again, so I'm going to take the sum from n equals 1 to infinity. Okay, 1 to infinity of the 1 all over 2n all squared. So this is the even term over here, right? That's what we're looking at, right? So this is the even, right? So now this is the even. Think about this, even and odd. That's what this problem is. Even and odd will give us our total sum that we're looking for. Okay, so let's simplify the even term. Notice that if we have this, actually I'll move this over. Right, so we're going to say summation from n equals 1 to infinity of 1 over 2n squared. Now I want you to notice, right, so notice the even term, okay? Notice that 2n all to the exponent 2, okay, is equal to 4n squared when I expand out the exponent, okay? Which means, right, obviously, if 2n all squared is equal to 4n squared, then logically this would mean that 1 all over 2n all squared is equal to 1 all over 4n squared. That 1/4 that I was talking about, the contribution of the Riemann zeta. Okay. So we can then say this. We can then say that the summation from n equals 1 to infinity, okay, of 1 all over 2n all squared, okay, is equal to the sum from n equals 1 to infinity of 1 all over 4n squared. All I'm doing is I just expanded out. I expanded out the exponent in. I distributed the exponent into the parentheses. Okay. Now this 1/4 can go in the front, right? Why can it go in the front? Well, it's a constant. It can go in front of the summation. So 1/4 times the summation from n equals 1 to infinity of 1 all over n squared. Well, look at that. Look what ends up happening here. I'm going to highlight this in yellow parentheses. You will notice, as I mentioned earlier, for those of you who've never seen it before, what that result is, that summation, right? What that summation is. It's the Riemann zeta function, pi is equal to pi squared over 6 on the first page. Oh, wait, that means I can substitute that in here, okay? So the obvious thing is to substitute pi squared over 6, okay? So now I'm going to say this becomes 1/4 times the pi squared times pi squared over 6. Okay, so I have the pi squared over 6 here, right? This is by Riemann zeta function. So this becomes pi squared over 24 then, because I'm multiplying pi squared over 24. Okay. That's a major relief point, actually, is that we've been able to calculate the sum from n equals 1 to infinity of 1 all over 2n all squared. Okay. We know what it is. We've gotten this part right here. Okay. This part right here, we've already finished the sum. Okay, we finished this sum here. So we've got that part. The even now the even terms are not at work, right? They are just a scaled copy of the original the Bessel sum, right? When I mean Bessel sum, I just mean the Riemann zeta function. Okay, so we found the even terms. Now we need to solve for the odd term. Okay, remember that's why I decomposed my Riemann zeta function into S of n and a Riemann zeta function multiplied by 1/4. That's what this is, right? With an exponent at 2. Because if I do that, then I have one that is an odd term and one is an even. That's the way to solve this problem. We found the even. We found the even expansion. We need to find the odd expansion. Okay, so I should highlight this. This is the even. It's the even term. The even terms. Okay, that's the even term. Now let's go to the odd terms. Okay, we're going to be looking at how to do solving for the odd term sum now. Okay, so we do the odd term. Also, if you're enjoying how this, the complexity of this problem, or you like solving the hard problems like this, put a thumbs up in the chat or anything else, any other comments you want. Okay, I appreciate it. So odd term. So we do the odd term sum. Odd term sum. Okay. So the odd term sum, right, was this one right here. So let's just rewrite everything. So we know that the summation from n equals 1 to infinity of 1 over n squared is equal to capital S of n, right? Capital S of n being that series, the 1 over 2n minus 1 all squared that we want to solve, plus the summation, okay, plus the summation from n equals 1 to infinity of 1 all over 2n all squared. Okay. Now we already figured out. Remember, this is the even. Found the even part. We found this is the even. Even. This is the odd. We want to figure out what the odd terms. Now we know that the summation from n equals 1 to infinity of 1 over n squared is pi squared over 6. So we could put that in. Right? We know that this is pi squared over 6. Okay. So left hand side is pi squared over 6. Riemann zeta. Pi squared over 6 is now equal to S of n. We don't know what S of n is. That's what we need to figure out. We need to figure out what S of n. But we have our even term now, the summation from n equals 1 to infinity of 1 over 2n all squared. Okay? We figured out what that was. That was pi squared over 24 based off the previous page, right? This result down here, right? So by the results on the previous page, we found that that was pi squared over 24. So the obvious thing is to solve for S of n. And guess what? That was what this question was asking. What is S of n, right? That's what we were looking to calculate. That's why I called it S of n in the first place. I mean, I could have kept the original sum, like the sum for n equals 1 to infinity of 1 over 2n minus 1 all squared, but I think that makes it more complicated and it makes it more messy. So sometimes we have to invent or create variables. Just keep track of all the variables and stay consistent. Okay, so we're going to move this over. So solving for S of n, so pi squared over 6 minus pi squared over 24 is now equal to S of n. Therefore, it's going to imply that S of n, right, implies that S of n is equal to, well, take a common denominator, so it becomes 20, sorry about that, it's going to be 4 pi squared minus, right, 6 pi squared, see, 4 pi squared, 6 pi squared, 6 pi squared, 24, okay? You get S of n to be simplified, it becomes minus 2 pi squared over 24. 2 over 24 is 112, so that becomes minus pi squared. Yeah, by 2 divided by 2. I'm getting, yes. Did I make a mistake somewhere? Did I make a mistake there, pi squared? I think I did a silly mistake. Where is it? Funny thing is, do advanced math, but then basic math is sometimes a problem. Let me see here. 4 pi squared, 4. Yeah. Yeah, this is 24. This is 6. So I only need to multiply 4. I need to have the 6 here. 4 pi squared minus pi squared, sorry. Minus pi squared gives me the 3 pi squared. Yeah, 3 pi squared over 24. 3 pi squared over 24 gives you, oh, pi squared over 8. Positive pi squared over 8. And that is our result. Okay, so S of n is equal to pi squared over 8. Okay. And since S of n, right, was the original sum that we were looking for, right? So because our original sum, right, S of n was equal to this, right, was equal to, just 1 second. I like making my sums look better. Okay, so sum from n equals 1 to infinity of 1 all over to n minus 1 squared, right? This is equal to S of n. Then this is equal to pi squared over 8. Okay. All right, and that is it. That is our answer to this problem. Okay, so as long as you follow a rigorous justification type of justification slash airtight step-by-step approach, and you connect things from definitions and terms that you already know, then even a problem like this can become simpler, right? I'm not doing anything brilliant here. I'm just doing, it's not that tricky. Okay. All right. Another thing I want to talk about here when it comes to something of this nature, right? Okay, when it comes to a problem like this, okay, just give me a moment. Yeah, what else did I want to talk about? I wanted to talk about something here that was very important. Well, there's one thing that's really interesting about problems like this, right? Is the satisfaction. This is one of those problems that feel much harder before you see the right viewpoint, right? And that's exactly why it is such a valuable exam type problem. I mean, just look at it. This is a perfect exam type problem. Okay, I think you would agree with me because the real skill being tested is not whether you can do like advanced algebra. That's not what it is, right? is whether you can take if you can take a complicated looking object and make it something you already know, right? Based off of definitions and principles that you already know, right? And that is what good mathematical problem solving is all about. You don't always need a brand new method, right? Sometimes you just need a better way of organizing what is already in front, right? Like grouping the terms, right? Grouping what you already know, and then from there, deductively reducing the problem, okay? And here, the entire problem turns on one simple insight. And that simple insight is what I mentioned. Odd terms equals full sum minus the even terms, right? That's how we were able to solve this, right? We took the odd terms, okay, equals the full sum. Let's put a sum here, minus the even terms, minus even terms. That's how we got our answer, okay? That was the whole game plan, okay? Now, I also want to talk about some interesting things here, right? Is that connecting the Bessel problem to the bigger picture? Okay, so what do I mean by that? Let's talk about why pi appears here at all. Why does the pi appear in this interesting summation? Well, especially if you haven't seen this before, you're probably thinking, "Sir, doesn't pi only appear when it comes to geometry with circles and stuff, right? Because pi is the circumference over the diameter." Right? So you're probably asking that if you haven't seen the summation before, right? Because as I said, law students feel uneasy about this. They think somehow that pi is the sum of rational looking terms. Where did the geometry sneak into this, right? As I mentioned, and some other things. And that's a very good instinct to have. But the reason why pi is showing up in what we use here, the formula that we use, the Riemann zeta definition, okay, is already deeply connected to calculus, trigonometry, and Fourier methods, right? So once you know the full sum contains that pi squared over 6, I'm zooming in on the pi squared, okay, on the pi squared, then splitting it into odd and even terms is not as mysterious anymore. That pi squared over 8 that we got for the original problem that we're trying to solve, that we're trying to prove anyways, is not that much of a surprise, given the fact that notice we have to notice that we have to use the Riemann zeta function, which is already dependent on the pi squared portion. Okay. And that perspective is useful because it helps you stop thinking of the results in terms of isolated tricks, if you know what I mean, right? So they're not isolated, right? Don't think that they're isolated, they're actually linked. Okay? And on exams, seeing those links is often what separates a student who stalls from a student who finishes on time, right? Right? Because you need to be able to see certain connections between the definitions and compare the definitions. Okay, that's very important, and then you'll be able to see how things fit. Now, the wrong approach to this, a very common wrong instinct, I'd like to talk about, right? Common wrong instinct when it comes to a problem of this nature. Okay, very common wrong instinct is that the student will see. I'll give you an example. The student will see the odd term sum and immediately think they need something to elaborate. They think they need automatically. I can guarantee that most of you, when you see the summation, you'll fall for the trap and use a Fourier um, expansion. Okay, you automatically think that it's a difficult Fourier series. You have to expand a special generating function or some trick that you've never seen before. Or you think you need to invent some new math, and all of that is completely wrong and completely nonsense. Sorry about that, but it's true. Okay. But if your exam problem can be solved, right? If your exam problem can be solved by recognizing the known sum and removing an even part, then you're on the right track. Okay. Right. So the emotional relief part I want to talk about is if you ever looked at a series like this and felt I'm not clever enough for these. I never would have guessed that it would be pi squared over 8. this kind of problem always feels out of reach, then I just want to say something very clearly. The point is not to guess the answer out of the air. The point is to see how to derive the answer, right? That is what mathematical maturity is. You need to be able to derive the answer. Don't guess it. Don't remember it from some page that you saw from a book somewhere. You need to know how to do it. Okay? Not instant insight, not magic, not memorized tricks, just calm deduction. That's what I like to call it. And when you start seeing problems that way, the hard exam questions stop feeling like random attacks, and you can start, um, maneuvering through complicated problems. Okay, that's the shift. Right? So if this, I just want to mention one last thing. If this style of explanation helps, where we take a hard undergraduate problem and make the structure visible, then that is exactly what this channel is about. That's what my channel is built for. Built for students who are taking mathematics, physics, engineering, or any other STEM related fields who want more than memorized steps. Okay. If you want to get stronger at hard midterm and exam questions in calculus, linear algebra, uh, any of the mathematical physics type topics, then this is the channel to subscribe with. Okay. Also, my book has very familiar problems like these. You can, if you're interested in trying them out, the link will be provided below. And if you want more rigorous visuals and step-by-step justified solutions like this, make your way through uh, and want to make your way through the other videos here. There'll also be a link to my, you know, tutoring tutoring services. All right. Again, like and subscribe. I hope you enjoyed the video, and I will see you in the next one. See you next week, guys. Bye bye.